Learning objectives. In this chapter, the user would learn the following in detail. Introduction to packaging of electronic systems, classification of packaging levels, packaging procedure, factors affecting packaging methods, study of electromechanical components, symbols, designations, and packaging styles, through-hole or surface mount devices, trends in packaging, study of types of wires and connectors, study of wiring harness design and manufacturing techniques, study of electronic standards IEEE, IEC, ANSI, ANSI. Case studies to learn various packaging levels or interconnecting techniques within the system. Case studies to learn various packaging levels, interconnecting techniques within the system. Case study of packaging levels. This case study is about product packaging and has examples of product packaging. So, what a design engineer should really look into if you are concerned with design of products from start to finish, including mechanical aspects. The first case study application area that we looked at was mobile phones or cellular phones. These are all the various items including the economic factors, cost, and so on. Manufacturing is related to cost. I think we are all very clear about these packaging aspects. The next part of case study or the next example that we looked at was personal computers. Personal computers including low-cost PC. I have mentioned you before a very important phenomenon. Depending upon the area, the cost of the product is determined through design. Accordingly, the materials are chosen for manufacturing. So, in personal computers, if it is a desktop computer, then you will get the designs to fix the cost. These automotive electronic system. Example of connection hierarchy, Blue Gene. It is a massive parallel supercomputer comprising of quad-core nodes. Nodes are basically very small, allowing for high packaging density in order to realize optimum cost reliability. Blue Gene uses 5 interconnection levels for input-output, debug, and various processes of inter-processor communication. It is used as a dynamic and deterministic routing with virtual buffering and cut-through capability. Classification of packaging levels. Level 0, gate-to-gate interconnections on the silicon die. Level 1, connections from the chip to its package. Level 2, PCB from component to component or to external connector. Level 3, connections between PCBs including backplanes or motherboards. Level 4, connections between sub-assemblies, for example, a rack. Level 5, connections between physically separate systems using, for example, an Ethernet LAN. Classification of packaging levels. Packaging levels are classified into 5 levels. Packaging levels. Level 0, monolithic silicon chip. Level 1, integrated circuits. Level 2, printed wiring board, PWB. Level 3, connection between PWBs. Level 4, subassembly. Level 5, connections between systems. Classification of packages as shown in figure. Wafer, electronic package hierarchy, chip, First level package, single chip module, first level package, multi-chip module, COB, second level package, PCB or card, third level package, motherboard. Level 0, gate-to-gate interconnection on the silicon die. Level 1, connection from the chip to its package. Level 2, PCB from component to component or to an external connector. Level 3, connections between PCBs including backplanes and motherboards. Level 4, connections between sub-assemblies, for example a rack. Level 5, connection between physically separate systems, example an Ethernet LAN. Advantages of electronic packaging system: circuit support and protection, controls performance of the system, also controls the cost of the system. It is used to reduce size of electronic components. Factors affecting electronic packaging system: electrical analysis and testing, mechanical analysis and testing, thermal analysis and testing, market analysis, reliability, performance and cost, microelectronics manufacturing infrastructure, research results from solid-state technology and other related fields of microelectronics, micromachining, wafer and chip bonding, mechanical material characteristics, sensor effects, actuator functions, integrated electronics, combination of features. Issues in electronic packaging system: electrical analysis and testing, mechanical analysis and testing, chemistry, physics, mathematics, engineering, reliability, performance, cost, market, need or timing, manufacturability, fields, others, thermal analysis and testing, manufacturing and industrial engineering, market analysis. Introduction to electronic packaging. What is electronic packaging system? It is the science or art of providing a suitable environment to an electronic product as a whole to function reliably over a period of time. Packaging of an electronic system should consider protection from mechanical damage, cooling, radio frequency noise emission, protection from electrostatic discharge, maintenance, operator convenience, and cost. Development of electronic packaging is a dynamic technology. Electronic packaging system also used in mobile telecommunication and satellite broadcasting to aerospace and automotive applications. Why electronic packaging system is important? It controls performance of computers, controls the size of consumer electronics, controls reliability of electronics, controls the cost of electronic products. Functions of electronic packaging. Major functions of electronic packaging. There are 4 major functions in electronic packaging system: signal distribution, power distribution, heat dissipation, and protection. Major functions of packaging: signal distribution, power distribution, heat dissipation or cooling, protection, mechanical, chemical, electromagnetic. Electronics packaging materials. Sheet metal. Punched and formed sheet metal is one of the oldest types of electronic packaging. It can be mechanically strong, provides electromagnetic shielding when the product requires that feature. Sheet metal is easily made for prototypes and small production runs with little custom tooling expense. Cast metal. Cast metal are used to package electronic equipment for exceptionally severe environments such as heavy industry, aboard ships, or deep underwater applications. Aluminum die castings are more common than iron or steel sand castings. Machined metal. Electronics packages are made by machining solid blocks of metal, usually aluminum, into complex shapes. Quantities tend to be small. Sometimes only one unit of a custom design is required. Piece part costs are high. Molded plastic. Molded plastic cases or structural parts are made by a variety of methods, offering trade-offs in piece part cost, tooling cost, mechanical and electrical properties. Easy assembly can be done. Potting. Normally called encapsulation, potting consists of immersing the part or assembly in a liquid resin and then curing it. Potting can be done in a pre-molded potting shell or directly in a mold. Porosity sealing or impregnation. Impregnation is similar to potting but does not use a shell or a mold. The main application of vacuum impregnation porosity sealing is in boosting the dielectric strength of transformers, solenoids, lamination stacks or coils, and some high voltage components. It is used to prevent ionization from forming between closely spaced live surfaces and initiating failure. Liquid filling. Liquid filling is used as an alternative to potting or impregnation. It is usually a dielectric fluid chosen for chemical compatibility with other materials present. This method is used mostly in very large electrical equipment such as utility transformers to increase breakdown voltage. It is used to improve heat transfer. Liquid filling can be easily removed for repair than potting. Conformal coating. Conformal coating is a thin insulating coating. It is used to provide mechanical and chemical protection for delicate components. It is widely used to mass produce items such as axial lead resistors and sometimes printed circuit boards. It can be very economical, difficult to achieve consistent process quality. Glob top. Glob top is an alternative type of conformal coating used in chip-on-board assembly. It consists of a drop of specially formulated epoxy and its wire bonds. It is used to provide mechanical support and exclude contaminants which could disrupt circuit operation. Hermetic metal or glass cases. Hermetic metal packaging started its life in the vacuum tube industry, where a totally leak-proof housing was essential for operation. Hermetic ceramic packages. Packages consisting of a lead frame embedded in a vitreous paste layer between flat ceramic top and bottom covers are more convenient than metal or glass packages for some products, but gives equivalent performance. Design considerations. An engineer or designer must balance many objectives and practical considerations when selecting a packaging method. Hazards to be protected against: mechanical damage, exposure to weather and dirt, electromagnetic interference, etc. Heat dissipation requirements, trade-offs between tooling capital cost and per unit cost, trade-offs between time to first delivery and production rate, availability and capability of suppliers, user interface design and convenience, ease of access to internal parts when required for maintenance, production safety and compliance with regulatory standards, aesthetics and other marketing considerations, service life and reliability. Reliability evaluation of electronics packaging system. A typical reliability qualification includes the following types of environmental stresses: burn-in, temperature cycling, thermal shock, solderability, autoclave, visual inspection, hermeticity or moisture resistance, packaging procedure. The manufacturing phase of an integrated circuit can be divided into two steps. The first, wafer fabrication, which is a sophisticated and intricate process of manufacturing the silicon chip. The second, assembly, which is a highly precise and automated process of packaging the die. These two phases are commonly known as front end and back end respectively. Manufacturing process of packaging system as shown in figure. Wafer fabrication followed by chip preparation, that is singulation, grinding, dicing, etc. Die bonding followed by wire bonding and transfer molding, and then trim and form. Chip preparation. A typical thickness for many compact packages today is approximately 0.5 mm, almost the same as standard wafer thickness, implying that most of the wafer backside will need to be removed to fit eventual outline. This process is called grinding. Next, the ICs are cut out of the wafer and can be used for further single processing. This is done at room temperature using a circular sawing or a laser cutting process sawing. Die bonding. The packaging process itself involves die attachment and encapsulation, with each cluster being a conglomerate of shapes and processes in itself. In the die bonding process, the single IC is attached on a carrier material, usually a metal called lead frame, by using some kind of polymeric die attachment materials, or in some cases by solder materials. Typical process temperature is 150 to 175 degrees Celsius for die attachment and up to 300 degrees Celsius for solid die attachment. Wire bonding. To connect the die to its environment, the basic choice is between wire bonding and flip chip technology. In a wire bonding process, the die is fixed into position with a metal-filled epoxy film or paste adhesive, or to allow operation to high die power dissipation through soldering. A continuous wire, usually gold, is connected to the first bond pad by ultrasound enhanced thermal compression, then stretched out and welded to the corresponding pin on the external connection structure. That structure will typically be a strip holding multiple patterns meant to be encapsulated in the molding process, the so-called lead frame. After the weld is made, the wire is cut with a flame of electric arc and brought next to the bond pad, restarting the sequence. In power applications, the thin gold wire may be replaced with a thick copper wire or by using aluminum straps. Wire bonding is still the major form of first-level interconnection in the world today. At present, over 95% of the manufactured packages in volume are wire bonded, and majority of the wire bonding is done with thermosonic gold ball bonding. A typical process temperature is 200 to 220 Celsius. Chip coating. For protection of the IC top surface, a chip coating material can be used. A chip coat is a highly viscous liquid or paste that encapsulates the IC, mostly epoxies or silicones with some inorganic filler. A typical process temperature is of 150 degrees Celsius. Transfer molding process. Transfer molding is the process most commonly used for die encapsulation. Epoxy resin liquefied by high temperature and pressure is forced through a mold chase over the die and the lead frame, and into the cavity on the frame where the die was placed earlier. The hardened epoxy eventually forms the body of the final package. In this process, the semiconductor IC, wires, and carrier are encapsulated by a epoxy-based material called epoxy molding compound EMC. The process temperature is about 175 degrees Celsius, followed by a 3 to 6 hours of curing step at 175 degrees Celsius. The EMC materials as well as the transfer molding process will be introduced in Chapter 3 in more detail. Mark, trim, and form. Finally, the packages are marked by a trim and form process where redundant materials are removed. After the IC packages are fabricated and qualified, they will be stored and transported until they are used for their final surface mount technology via a soldering process to mount these devices on the printed circuit board. Reflow soldering is the most common method of attaching IC packages and other surface mount components on a circuit board. The goal of a reflow process is to melt the solder alloy particles within the solder paste without overheating or damaging the electrical components. Heating may be accomplished by passing the assembly through a reflow oven or under an infrared lamp, or by soldering individual joints with a hot air pencil. Today, environmental considerations force the so-called lead-free solder materials and the removal of lead materials from microelectronics systems. The materials used so far for soldering are conventional PBSN eutectic soldering materials that induce automatic alignment of a misplaced or non-flat die by surface tension. This phenomena, together with quite limited temperature budget imposed by advanced SI wafer technologies, limits the range of reliable alternatives. Packaging. What is packaging? Wrapping or protecting the products for distribution, storage, sale and use. It refers to process of design, evaluation and production of packages. Importance of packaging. It plays an important role while attracting customers towards the product. It motivates the customers in international markets. Sometimes, packaging is more important than its cost and product also. Purpose of packaging: physical protection, barrier protection, containment, information transmission, marketing, security, convenience, and portion control. Packaging is every technology required between IC and system. Without proper packaging, manufactured item is not as good. Packaging types. Packaging types are primary, secondary, and tertiary. Primary packaging: it envelopes the product and holds it. It is the smallest unit of distribution or use and is the package which is in direct contact with the contents. Secondary packaging: outside of primary packaging, perhaps used to group primary packages together. Tertiary packaging: it is used for bulk handling, warehouse storage, and transport shipping. Common form is pelletized unit load that packs tightly into containers. Packaging is the outer container that allows easier handling during transfer between factories, distribution centers, and retailers. Symbols used on packages. For consumer packaging, symbols are used for product certification, trademarks, proof of purchase, etc. Barcodes, universal product codes, and RFID labels are allowed automated information management in logistics and retailing. Symbols are used to communicate aspects of consumer rights and safety. Study of electromechanical components, symbols, designations, and packaging styles. Electromechanical: it is defined as relating to or begin a mechanical process or device actuated or controlled electrically. Electromechanical device acts as a transducer for converting electrical energy to a mechanical energy. Electromechanics: in engineering, electromechanics combines electrical and mechanical processes and procedures drawn from electrical engineering and mechanical engineering. Devices which carry out electrical operations by using moving parts are known as electromechanical devices. A device which involves an electrical signal to create mechanical movement or mechanical movement to create electrical signal. Electromechanical components uses. Electromechanical components are used in complicated systems and subsystems, electrical typewriters, teleprinters, television systems, and electromechanical digital computers. Electromechanical symbols or relays. The most common schematic symbols used in electromechanical systems are crossed wire or no connection, Gottlieb no connect, others connected, crossed wires connected, wall plug or AC supply, fuse, score motor, light bulb, ground. Normally open switch, normally closed switch, make or break switch. Resistor, capacitor, coil or solenoid or relay coil, transformer, stepper unit. An electric current through a conductor will produce a magnetic field at right angles to the direction of electron flow. If that conductor is wrapped into a coil shape, the magnetic field produced will be oriented along the length of the coil. Greater the current, greater is the strength of the magnetic field, all factors being equal. Inductors react against changes in the current because of the energy stored in the magnetic field. When constructing a transformer from two inductor coils around a common iron core, it uses this field to transfer energy from one coil to another. However, there are simpler and more direct uses of electromagnetic field than the application have been seen with inductors and transformers. The magnetic field produced by a coil of a current carrying wire can be used to exert a mechanical force on any magnetic object. A permanent magnet is used to attract magnetic objects, except that this magnet formed by a coil can be turned on or off by switching the current on or off through the coil. A solenoid. If we place a magnetic object near such a coil for the purpose of making that object move, when we energize the coil with electric current, it is called a solenoid. The movable magnetic object is called an armature. Armatures can be moved with either direct current DC or alternating current AC, energizing the coil. The polarity of the magnetic field is irrelevant for the purpose of attracting an iron armature. Relays are used to control a large amount of current or voltage with a small electrical signal. The relay coil, which produces the magnetic field, may only consume fractions of a watt of power, while the contacts closed or open by the magnetic field may be able to conduct hundreds of times that amount of power to a load. In effect, a relay acts as a binary on or off amplifier. In the above schematic, the relay's coil is energized by the low voltage of 12 volt DC source, while the single pole single throw SPST contact interrupts the high voltage of 480 volt AC circuit. One relay coil or armature assembly may be used to actuate more than one set of contacts. These contacts may be normally open, normally closed, or any combination of the two. Relay contacts may be open air pads of metal alloy, mercury tubes, or magnetic reeds, just as with other types of switches. The choice of contacts in a relay depends on the same factors which dictate contact choice in other types of switches. Open air contacts are the best for high current applications, but their tendency to corrode and spark may cause problems in some industrial environments. Mercury and reed contacts are sparkless and won't corrode, but they tend to be limited in current carrying capacity. Shown here are three small relays, about 2 inches in height each, installed on a panel as a part of electrical control system at a municipal water treatment plant. The relay units are called octal bays because relays are plugged into matching sockets. The electrical connections are secured via 8 metal pins on the relay bottom. This type of construction facilitates easy removal and replacement of the relay in the event of failure. Aside from the ability to allow a relatively small electric signal to switch a relatively large electric signal, relay also offers electrical isolation between coil and contact circuits. This means that the coil circuit and contact circuits are electrically insulated from each other. One circuit may be DC and the other AC, such as in the example circuit shown earlier, and or they may be completely different voltage levels across the connections or from the connections to the ground. While relays are essentially binary devices, either being completely on or completely off, their operating conditions where their state may be indeterminate, just as with semiconductor logic gates. Pull-in current. In order for a relay to positively pull in the armature to actuate the contacts, there must be a certain minimum amount of current through the coil. This minimum amount is called pull-in current, and it is analogous to the minimum input voltage that a logic gate requires to guarantee a high state, typically 2 volts for TTL and 3.5 volts for CMOS. Once the armature is pulled closer to the coil center, however, it takes less magnetic field flux, less coil current to hold it there. Dropout current. The coil current must drop below a value significantly lower than the pull-in current before the armature drops out to its spring-loaded position and the contacts resume their normal state. This current level is called the dropout current, and it is analogous to the maximum input voltage that a logic gate input will allow to guarantee a low state, typically 0.8 volts for TTL and 1.5 volts for CMOS. The hysteresis or difference between pull-in and dropout currents results in operation that is similar to a Schmidt trigger logic gate. Pull-in and dropout currents and voltages vary widely from relay to relay and are specified by the manufacturer. Electromechanical packaging styles. 1. Through-hole package. 2. Surface mount package. 3. Chip scale package. Through-hole technology. Through-hole technology is a mounting scheme used for electronic components that involves the use of leads on the components that are inserted into holes drilled in the printed circuit boards and soldered to the pads on the opposite side, either by manual assembly, hand placement, or by the use of automated insertion mount machines. Through-hole devices were mounted on the circuit board of a mid-1980s home computer. Axial lead devices are at upper left, while the blue radial lead capacitors are at the upper right. Pins of the components go through the previously drilled PCB holes. History of through-hole. Through-hole technology almost completely replaced earlier electronic assembly techniques such as point-to-point construction. From the second generation of computers in the 1950s until surface mount technology (SMT) became popular in the 1980s, every component on a typical PCB was a through-hole component. PCBs initially had tracks printed on one side only. Later, both sides, then multi-layer boards were used. Through-holes became plated through-holes (PTH) in order for the components to make contact with the required conductive layers. Plated through-holes are no longer required with SMT boards for making the component connections, but are still used for making interconnections between layers, and in this role are more usually called vias. Through-hole mount packaging is shown. Through-hole benefits. Sinclair ZX48 motherboard is shown in figure. Easy to solder either automatically or by hand. Easy to desolder and test. Implement interconnections between upper and lower layers vias in a non-plated hole technologies. Through-hole drawbacks. Signals must be necessarily going through all PCB layers. Low density due to minimum pin diameter and only one side mounting. Surface mount technology. method of producing electronic circuits in which the components are mounted or placed directly onto the surface of a printed circuit board, PCBs. An electronic device so made is called a surface mount device, SMD. In the industry, it has largely replaced the through-hole technology construction method of fitting components with wire leads into the holes in the circuit boards. Both technologies can be used on the same board, with the through-hole technology used for components not suitable for surface mounting, such as large transformers and heat-sinked power semiconductors. An SMD component is usually smaller than its through-hole counterpart because it has either smaller leads or no leads at all. It has short pins or leads of various styles, flat contacts, or a matrix of solder balls, BGAs, or terminations on the body of the component. The pins of the devices are mounted directly onto the surface of the PCB. Surface mount assembly technologies. Where components are to be placed, the printed circuit board normally has flat, usually tin lead silver or gold plated copper pads without holes called solder pads. Solder paste, a sticky mixture of flux and tiny solder particles, is first applied to all the solder pads with stainless steel or nickel stencil using a screen printing process. It can also be applied by a jet printing mechanism similar to an inkjet printer. After pasting, the boards then proceed to a pick and place machine where they are placed on the conveyor belt. The components to be placed on the boards are usually delivered to the production line in either paper or plastic tapes wound on reels or plastic tubes. Some larger integrated circuits are delivered in a static free tray. Numerical control pick and place machines remove these parts from the tapes, tubes or trays and place them on the PCB. Reflow soldering. The boards are then conveyed into a reflow soldering oven. They first enter a preheat zone where the temperature of the board and all the components is gradually and uniformly raised. The boards then enter a zone where the temperature is high enough to melt the solder particles into solder paste, then bonding the component leads to the pads on the circuit board. The surface tension of the molten solder helps to keep the components in place, and if the solder pad geometries are correctly designed, surface tension automatically aligns the components on their pads. Techniques of reflow soldering. There are a number of techniques for reflow soldering. One is to use infrared lamps. This is called infrared reflow. Another is to use hot gas convection. Another technology which is becoming popular again is a special fluorocarbon liquids with high boiling points, which uses a method called vapor phase reflow. If the circuit board is double-sided, then this printing, placement and reflow process may be repeated using either solder paste or glue to hold the component in place. If a wave soldering process is used, then the parts must be glued to the board prior to processing to prevent them from floating off when the solder paste holding them in place is melted. Removal of surface mount using soldering. After soldering, the boards may be washed to remove flux residues and any stray solder balls that could short out closely spaced component leads. Resin flux is removed with fluorocarbon solvents, hydrocarbon solvents with high flash point or low flash point. However, most electronic assemblies are made using a no-clean process where the flux residues are designed to be left on the circuit board benign. This saves the cost of cleaning and speeds up the manufacturing process, thus reducing waste. Proper cleaning removes all traces of solder flux as well as dirt and other contaminants that may be invisible to the naked eye. However, while shops conforming to IPC standards are expected to adhere to the association rules on the board condition, not all manufacturing facilities apply IPC standard nor are they required to do so. Additionally, in some applications such as low-end electronics, such stringent manufacturing methods are excessive both in expense and time required. Benefits of surface mount technology. Exact surface mount technology. Much higher density. Pins can be thinner. Devices can be mounted on both sides of the PCB. Components do not block signals in the inner layers. High degree in automation of mounting process. Less parasitic inductance and capacitance. Reduced cost half to 1/4 and size 1/4 to 1/10. Drawbacks of surface mount technology. Poor manual solderability and repairability. Reliability issues due to thermal and mechanical stress during soldering and operation. Different thermal expansion coefficients. Classic verification procedures are no longer valid. Chip scale packages. Chip scale packages or CSP based on IPC/JEDECJ STD012 definition is a single die direct surface mountable package with an area of no more than 1.2 times the original die area. Chip scale technologies is shown in figure. CSP is not a new mounting technology. It is an evolution of SMD. The passive components surrounding the chip must also be miniaturized: resistors, decoupling capacitors. CSP benefits and drawbacks. Benefits. CSP is the only way to achieve a pervasive and ubiquitous computing. Further improvement in high-speed performance. Drawbacks. Difficulty of PCB fabrication and mounting due to minute pin pitches 0.5 mm. Long-term reliability not studied. Not serviceable. 3 packages breakthrough in packaging technology is shown in graph. X-axis year 1980-2000, y-axis volume, density. Through-hole, DIP, pin grid, surface mount, QFP, TSOP, SQJ, BGA, chip scale, CSP, wafer level, stacked die. First step of packaging, the silicon wafer. The problem: how do I know that the chip is going to work before packaging it? Solution: test it. But this is a note as how to achieve it. Probing pads 150 micrometer away, area array pads, powering the chip, removing the heat it generates. Testing it in a reasonable time. Only a limited testing, if any, is usually performed. Full testing is done after the packaging. A typical low-density SMD process from silicon wafer to package is shown. Assembly process flow: wafer preparation, dicing, die attachment, wire bonding, molding, solder plating, marking, followed by lead trimmer form. Wafer preparation and dicing. Wafers are mounted on a laminating tape that adheres to the back of the wafer. It holds the wafer throughout the dicing and the die attachment process. The die sawing machine, using a diamond saw blade, saws the wafer into the individual die or pellet on the adhesive backing tape. Deionized water and CO2 bubbles are dispensed on the wafer to remove silicon dust or debris, besides lubricating and cooling down the blade. Die attachment and wire bonding. The die attachment machine will pick up the die and deposit it on the frame. It may utilize the wafer mapping method to pick up only good die. For most processes, die attachment materials like gold or lead tin based solder wires or silver epoxy paste potting on the frame are required prior to the die bonding process. Either gold or aluminum wires are used depending on the application. Bonded one at a time, the wire is fed through a ceramic capillary. With a good combination of temperature and ultrasonic energy, a good metallized wire bond is formed. Molding and solder plating. The molding process aims to encapsulate the whole wire bonded die against exposure to contamination and other physical damages. The lead frames that holds the die are placed in individual cavities which are filled with liquid resin. This step provides a layer of tin lead solder on the lead frame for making easier the PCB assembly process. Lead-free finishing with tin bismuth plating or tin copper dipping can also be done. Marking and lead trim or form. Marking is the coding process that writes customers' corporate and product identification code on a packaged device. It commonly uses a laser-based machine. The final process is to trim away the leads of the packaged device from the frame strip. The leads are cut and formed mechanically to the specified shape. Chip attachment to the package substrate. The die attachment compound should provide electrical grounding and thermal dissipation. There are three alternatives. Soft solder die attachment. This process uses a solder material to bond the die to the lead frame. The solder is introduced as a wire and melted onto the hot lead frame surface as a liquid solder dot. Epoxy die attachment. Epoxy die attachment is the most commonly used process. Usually, silver-loaded polymers are used, but the term generally encompasses the use of other adhesives such as polyimide or silicon-based materials. Metal-filled glasses. Less used because the high temperature needed, but have been used in ceramic packages. Chip package connection, that is wire bonding. Connections are made from the chip to the pad frame via thin wires. Typically 100 by 100 micrometer metal pads on 200 micrometer pitch. Mechanical bonding of one pin at a same time, sequential. The wires are made of low resistivity alloys or doped metals. Gold and aluminum, also copper and silver. Typically 25 micrometer diameter for logic devices. Drawbacks of wire bonding. Slow process, one pin at a time. Speeds from 4 to 10 wires per second. Pads are limited to the chip periphery. Low pad density and reduced pad pitch. Up to approximately 500 pads. Electrical limitations. High inductance, approximately 1 Nh of wires, approximately 10 Nh plus pins. Crosstalk between adjacent wires. Chip package connection. Chip package connection tab. Tape automated bonding. The interconnections are patterned on multilayer polymer tape. The tape is positioned above the bare die so that the metal tracks on the polymer tape correspond to the bonding sides on the die. Advantages over wire bonding: smaller and closer pads, higher density up to 850 pins, better electrical characteristics, faster procedure but more expensive machinery. Chip package connection, flip chip. The chip is soldered to the package substrate using the solder balls, bumps that have been grown over the die pads. Flip chip advantages and drawbacks. Flip chip is currently the preferred process for high-end integrated circuits. High frequency of operation, small size and/or many input-output pins. Many advantages. Improved density, pad pitch and size is not better than in wire bonding, but input-output pads can be distributed all over the die, not just in the borders. Reduced inductance, approximately 0.1 Nh, due to the elimination of wires and better power or ground behavior. Faster process, all the pads are soldered at the same time. Some drawbacks. Alignment in critical and blind, although there is some tolerance due to its self-alignment property. Mechanical stress due to different thermal expansion coefficients of the silicon and the package substrate. Study of electronic standards IEEE, IEC, ANSI. Electronic standards IEEE. IEEE. The Institute of Electrical and Electronics Engineers Standards Association IEEE.SA. An organization within IEEE that develops global standards in a broad range of industries. It includes power and energy, biomedical and healthcare, information technology and robotics, telecommunication and home automation, transportation, nanotechnology, information assurance, and many more. IEEE.SA has developed standards for over a century through a program that often balances openness, fair procedures, and consensus. Technical experts from all over the world participate in the development of IEEE standards. IEEE.SA is not a body formally authorized by any government but rather a community. Formally recognized international standards organization ISO, IEC, ITU, CEN are federations of national standards bodies. American ANSI, German DIN, Japanese JISE, etc. Standards and the IEEE standards development process. Each year, the IEEE.SA conducts over 200 standards ballots, a process by which proposed standards are voted upon for technical reliability and soundness. In 2005, IEEE had close to 900 active standards with 500 standards under development. One of the more notable are the IEEE 802 LAN/MAN group of standards with the widely used computer networking standard for both wired Ethernet aka IEEE 802.3 and wireless IEEE 802.11 and IEEE 802.16 networks. The IEEE standards development process can be broken down into 7 basic steps. Securing sponsorship. An IEEE approved organization must sponsor a standard. A sponsoring organization is in charge of coordinating
and supervising the standard development from inception to completion. The professional societies within IEEE serve as the natural sponsor for many standards. Requesting project authorization. To gain authorization for the standard, a project authorization request (PAR) is submitted to the IEEE SA Standard Board. The new Standards Committee (NESCOM) of the IEEE SA Standards Board reviews the PAR and makes a recommendation to the Standards Board about whether to approve the PAR. Assembling a working group. After the PAR is approved, a working group of individuals affected by or interested in the standard is organized to develop the standard. IEEE SA rules ensure that all working group meetings are open and that anyone has the right to attend and contribute to the meetings. Drafting the standard. The working group prepares a draft of the proposal standard. Generally, the draft follows the IEEE Standard Style Manual that sets guidelines for the clauses and format of the standards document. Balloting. Once a draft of the standard is finalized in the working group, the draft is submitted for balloting approval. The IEEE Standards Department sends an invitation to ballot to any individual who has expressed an interest in the subject matter of the standard. The IEEE requires that a proposed draft of the standard receives a response rate of 75%, that is, at least 75% of the potential ballots are returned, and that of the responding ballots, at least 75% approve the proposed draft of the standard. If the standard is not approved, the process returns to the drafting of the standard step in order to modify the standard document to gain approval of the balloting group. Review Committee. After getting 75% approval, the draft standard along with the balloting comments are submitted to the IEEE SA Standards Board Review Committee (RevCom). The RevCom reviews the proposed draft of the standard against the IEEE SA Standards Board bylaws and the stipulations set forth in the IEEE SA Standards Board Operations Manual. Final vote. Each member of the IEEE SA Standards Board places a final vote on the submitted standard document. In some cases, external members are invited to vote. It takes a majority vote of Standards Board to gain final approval of the standard. In general, if the RevCom recommends approval, the Standards Board will vote to approve the standard.
Electrical Standards (IEC). The International Electrotechnical Commission (IEC) in French, Commission Electrotechnique Internationale. It is a non-profit, non-governmental international standards organization that prepares and publishes international standards for all electrical, electronic, and related technologies, collectively known as electrotechnology. IEC standards cover a vast range of technologies from power generation, transmission, and distribution to home appliances and office equipment, semiconductors, fiber optics, batteries, solar energy, nanotechnology, and marine energy, as well as many others. The IEC also manages 3 global conformity assessment systems that certify whether equipment, system, or components conform to its international standards. The IEC Charter embraces all electro technologies, including energy production and distribution, electronics, magnetic and electromagnetic, electroacoustics, multimedia, telecommunication and medical technology, as well as associated general disciplines such as terminology and symbols, electromagnetic compatibility by its advisory committee on electromagnetic compatibility ACEC, measurement and performance, dependability, design and development, safety and environment. IEC standards. IEC standards have numbers in the range of 60000 to 79999, and their titles take a form such as IEC 60417, graphical symbols for use on equipment. The number of older IEC standards were converted in 1997 by adding 60000. For example, IEC 27 became IEC 60027. The IEC are cooperated closely with the International Organization for Standardization ISO and the International Telecommunication Union ITU. In addition, it works with several major standards development organizations, including the IEEE, with which it signed a cooperation agreement in 2002, which was amended in 2008 to include joint development work. Standards developed jointly with ISO, such as ISO/IEC 26300, Open Document Format for Office Applications, Open Document, version 1.0, carry the acronym of both organizations. The use of the ISO IEC prefix covers publications from ISO IEC Joint Technical Committee 1, Information Technology, as well as conformity assessment standards developed by ISO CASCO and IEC CAB Conformity Assessment Board. Other standards developed in cooperation between IEC and ISO are assigned numbers in the 80000 series, such as IEC 820451. The 60000 series of standards are also found preceded by EN to indicate the IEC standards harmonized as European standards. For example, IEC 60034 would be EN 60034. IEC standards are also being adopted as harmonized standards by other certifying bodies such as BSI, United Kingdom, CSA, Canada, UL and ANSI or INCITS, United States, SABS, South Africa, SAI, Australia, SPC/GB, China, and DIN, Germany. IEC standards harmonized by other certifying bodies generally have some noted differences from the original IEC standard. Electrical Standards, ANSI. The American National Standards Institute, ANSI, is a private non-profit organization that oversees the development of voluntary consensus standards for products, services, processes, systems, and personnel in the United States. The organization also coordinates US standards with international standards so that American products can be used worldwide. ANSI standards are developed by representatives of other standards organizations, government agencies, consumer groups, companies, and others. These standards ensure that the characteristics and performance of products are consistent, that people use the same definitions and terms, and that products are tested in the same way. ANSI also accredits organizations that carry out product or personal certification in accordance with requirements defined in international standards. The organization's headquarters are in Washington, D.C. ANSI Operations Office is located in New York City. The ANSI annual operating budget is funded by the sale of publications, membership dues and fees, accreditation services, fee-based programs, and international standards programs.
Study of types of wires and connectors. Study of electrical wires. A wire is a single, usually cylindrical, flexible strand or rod of metal. Wires are used to bear mechanical loads or electricity and telecommunication signals. Wire is commonly formed by drawing the metal through a hole in a die or a draw plate. Uses. It is used for transmission of electricity or electrical signals. Electricity in long wires used in transmission behaves very differently than in short wires used in design of devices. The use of wires in AC circuits brings on all sorts of problems like skin effect and proximity effects, resistivity or impedance, skin effect, types of wire design, more on wire materials, wire insulation. Behavior of electricity in wires, resistance and impedance. It is important to know if you are dealing with DC or AC power in a given wire. AC power has some very complex physics which causes some strange effects. AC power. AC power current tends to travel near the surface of a wire. Skin effect. AC power in a wire also causes a magnetic field to form around it. Inductance. This field affects other nearby wires such as in a winding, causing proximity effect. All of these properties must be dealt with when designing an AC circuit. DC power. In DC power, current travels to the whole wire. Size of the conductor and material, AC and DC power. Electricity travels more easily in highly conductive elements like copper, silver or gold. The less conductive materials, the larger the diameter has to be to carry the same amount of current. Quality of material, impurities and crystals. Most materials have impurities. In copper, the oxygen content and other materials in copper affect the conductivity. So, copper which is used for electrical wire is alloyed differently than copper which is used for plumbing. Metals are crystalline, as you'll see in copper video.
Monocrystalline copper or aluminium has better conductivity than polycrystalline metals. However, large crystal copper is very expensive to produce and only used in high-performance applications.
Resistivity. Resistance in a wire describes the excitation of electrons in the conductor. The excitation results in the creation of heat and loss of efficiency. Measurement tools. Ohm's law is used to calculate how much resistance a given wire will have. This tells us how much energy we will lose over distance. I is equal to V by R amps. is equal to volts divided by resistance. Formula for resistance and conductance. Resistance is equal to resistivity divided by cross-sectional area. Conductance is equal to 1 by resistance. Magnetic fields, inductance and impedance. Every wire that transmits AC power creates a magnetic field while current flows through it. The magnetic field is visualized by concentric rings around the cross-section of the wire. Each ring closer to the wire has a stronger magnetic power. Skin effect. In AC power, electrons like to flow on the outside of the wire. This is because the changing of current back and forth causes eddy currents that results in current crowding towards the surface. Skin effect in a solid wire. Core of wire carries little current. More current travels on the outside surface. Skin depth. Skin depth is a fixed number for a given frequency, resistivity and permittivity. The higher the frequency of the AC power in a system, the more current is compressed on the outside of the wire. So, a wire that is used at 60 Hz at a given voltage will not be okay at 200 MHz. Skin effect in insulated. Back insulation. Types of wire. Solid wire. Solid wire, also called solid core or single strand wire, consists of one piece of metal wire. Solid wire is useful for wiring breadboards. Solid wire is cheaper to manufacture than standard wire and is used where there is little need for flexibility in the wire. Solid wire also provides mechanical ruggedness, and because it has relatively less surface area which is exposed to attack by corrosives, thus protecting it against the environment. Stranded wire. Stranded copper wire. Stranded wire is composed of a number of small wires bundled or wrapped together to form a larger conductor. Stranded wire is more flexible than solid wire of the same total cross-sectional area. Stranded wire tends to be a better conductor than solid wire because the individual wires collectively comprise a greater surface area. Stranded wire is used when higher resistance to metal fatigue is required. Braided wire. A braided wire is composed of a number of small strands of wire braided together. Similar to stranded wires, braided wires are better conductor than solid wire. Braided wires do not easily break when flexed. Braided wires are often suitable as an electromagnetic shield in noise reduction cables. Electrical connectors. Electrical connector is an electromechanical device for joining electrical circuits as an interface using a mechanical assembly. Connectors consist of plugs, male end, and jacks, female end. There are hundreds of types of electrical connectors. Connectors may join two lengths of flexible copper wire or cable, or connect wire or cable to an electrical terminal. Properties of electrical connectors. Electrical connectors are characterized by their pin out and physical construction, size, contact resistance, insulation between pins, ruggedness and resistance to vibration, resistance to any entry of water or other contaminants, resistance to pressure, reliability and lifetime. It is usually desirable for a connector to be easy to identify visually, rapid to assemble, require only simple tooling, and be inexpensive. Types of electrical connectors. A terminal is a simple type of electrical connector that connects two or more wires to a single connection point. Wire nuts are another type of single point connector. Terminal blocks. Terminal blocks of various types. Terminal blocks, also called terminal boards or strips, provide a convenient means of connecting individual electrical wires without a slice or physically joining the ends. They are usually used to connect wiring among various items of equipment within an enclosure or make connections among individual enclosed items. One type of terminal block accepts wires that are prepared only by stripping a short length of insulation from the end. Another type accepts wires that have ring or spade terminal lugs crimped onto the wire. Printed circuit board (PCB) mounted terminal blocks allow individual wires to be connected to the circuit board. PCB mounted terminal blocks are soldered to the board, but they are available in a pull-apart version that allows the wire connecting half of the block to be unplugged from the part that is soldered to the PCB. Plug and socket connectors. Plug and socket connectors are usually made up of male plug, typically pin contacts, and a female receptacle, typically socket contacts, although hermaphroditic connectors exist, such as the original IBM token ring LAN connector. Plugs generally have one or more pins or prongs that are inserted into the openings in the mating socket. The connection between mating metal parts must be sufficiently tight to make a good electrical connection and complete the circuit. When working with multi-pin connectors, it is helpful to have a pin-out diagram to identify the wire or circuit node connected to each pin. Jack. Jack commonly refers to a connector, often with a female electric contact or socket, and is more fixed connector of a connector pair. Plug. Plug commonly refers to a movable connector, often but not always, with a male electrical contact or pin, and is movable, less fixed connector of a connector pair. Component and device connectors. High power transistor switch module with large screw connectors and small crimped on fast on connectors. Electrical and electronic components or devices sometimes have plug and socket connectors or terminal blocks, but individual screw terminals and fast on or quick disconnect terminals are more common. Small components have bare lead wires for soldering. They are manufactured using casting. Blade connector. Blade connectors, lower half of the photo. Ring and spade terminals, upper half of the photo.
Bullet terminals, male and female.
Right center with blue wires. A blade connector is a type of single connection wire using a flat conductive blade which is inserted into a blade receptacle. Usually, both blade connector and blade receptacle have wires attached to them either through the wire of the blade or crimping of the blade to the wire. Ring and spade terminals. Ring style wire and blade connectors are normally sold in lots. The connectors in the top row of the image are known as ring terminals and spade terminals, sometimes called fork or split ring terminals. Electrical contact is made by the flat surface of the ring or spade, while mechanically they are attached by passing a screw or bolt through them. The spade terminal form factor facilitates connection since the screw or bolt can be left partially screwed in as the spade terminal is removed or attached. Their sizes can be determined by the size of the conducting wire AWG and the screw or bolt diameter size designation. Printed circuit boards are called as printed wire boards. The board's base for physically supporting and wiring the surface mounted and socketed components is most important in electronics. Study of wiring harness design and manufacturing techniques. Wiring harness. Cable harness is also called as wire harness. Assembly of cables or wires which transmit the signal or electric power. The cables are bound together by straps, cable ties, cable lacing, sleeves, electrical tape, conduct, a weave of extruded string or a combination thereof. A wiring harness is an organized set of wires, terminals and connectors that run throughout the entire vehicle and relay information and electric power, thereby playing a critical role
in connecting a variety of components.
Power and information travel through this network much like the circulatory and central nervous systems of the body. Wiring harness components: wires, terminals, connectors, caps and sleeves, fuse boxes. Wiring harness consists of various wires bundled together with each individual wire responsible for carrying the electrical signals and energy used in starting the engine, light meters, navigation systems, power windows and doors, and other devices in the vehicle. Wires. Wire is a single, usually cylindrical, flexible strand or rod of metal used to bear mechanical loads and to carry electricity and telecommunication signals. Connectors. In their role of connecting wires and cables within an automobile, connectors must function in environments with extreme temperature variations, vibrations, water, electromagnetic interference, and other conditions. The increased use of information technology has developed a variety of connectors and other components that connect wires to GPS, TV, and other wave receiving devices in today's automobiles. Terminals. Terminals are the current carrying connection points between the wires and the features in the automobile. Made of a variety of metals, these parts can be coated differently to meet a number of conditions. Caps and sleeves. Caps. Caps are used to protect the terminals from being damaged. Sleeves. Sleeves are used to protect the wires from shrinking due to high currents. Fuse boxes. To protect the wire lines from short when high intensity of current is passed. Wiring harness manufacture. Step 1. Terminals are fixed on wires, then with the help of applications, wires are cut on CNC machines. Step 2. Quality of the wire is being checked by the quality analyst. Parameters to be checked: PVC of the wire, terminations of the wire, width of the terminal. Step 3. Tapping is done on the wires to protect them from moisture and heat. After tapping, quality is checked. Then packing is done. Finally, products are dispatched to the market. Trends in packaging. Trends in
Electronic packaging system.
An overview is given of trends in electronic packaging and assembly for portable consumer products. With regard to components, the focus is on thinner and smaller packages with a higher lead count. To save board space, integrated passive components in CSP format are being developed. The use of modules that provide a complete function is increasing. Advantages: flexibility, diversity, cheaper, simpler second-level assembly. The high-density interconnect is limited to the interior of the module. Both motherboards and interposer substrates used in packages and modules are characterized by smaller features to accommodate higher input-output density and reduce thickness to limit the overall electronic assembly height. For the same reasons, techniques and materials have been developed to enable embedded passives. New substrate materials have been developed with better electrical and thermal behavior to comply with the RF requirements. In assembly processes, package assembly is done increasingly at wafer or substrate level to save costs, increase production, and facilitate package miniaturization. Standard reflow soldering is optimized to enable the integration of CSPs and flip chips on the motherboard. In some areas, conductive adhesive is used. Finally, due to the market demand and legislation, assembly processes, components and materials must be adapted to realize environmentally friendly products. Special attention is paid to the elimination of lead volatile organic components. Stages in the development of packaging technology. The development of electronic packaging goes through various stages, which are environment, building blocks, enabling technology, modeling and simulation, comparison to specifications, iteration, preparation for manufacturing.
Conclusion. In this chapter, we have covered the following in detail. Introduction to packaging of electronic systems, classification of packaging levels, packaging procedure, factors affecting packaging methods, study of electromechanical components, symbols, designations, and packaging styles, through-hole or surface mount devices, trends in packaging, study of types of wires and connectors, study of wiring harness design and manufacturing techniques, study of electronic standards IEEE, IEC, ANSI, ANSI. Case studies to learn various packaging levels or interconnecting techniques within the system.